MSc. So his expertise is in operator algebras, non-commutative geometry, and K theory. So today he's going to talk on multiparameter E0 semigroups. So over to you, Sundar.
Yeah. Thanks a lot. Thanks for the invitation. I thank Suratno and Biswas for arranging this talk and many others. So let me share my screen and then I will start my talk. So, is the screen visible to everyone?
Yes.
Yeah.
Okay. So, oops, sorry. I think I have given slideshow. Let me quit presentation. Okay. So, this subject of multiparameter E0 semigroup is a recent thing that we have been doing for a while in collaboration with a couple of students and others. The E0 semigroup is a theory that is well developed for the last 30 years. Any disturbance? Can anyone hear me? Can everyone hear me? Yeah. So the E0 semigroup is a theory that is sort of well developed over the last 30 years, and two names stand out. One is R.T. Powers and another is William Arverson. William Arverson was a leading operator algebraist, and he is well known for his work in his work is fast, and one of the closest areas, one of the areas that he worked very extensively is E0 semigroups. Okay, and so today's talk is about multiparameter E0 semigroups. So I'll explain what it is. So let me go to the first slide. So I'm going to talk in a slightly more general context, but you can assume without loss of generality, we can assume certain things. So for me, G is a locally compact second countable Hausdorff topological group. So for example, locally compact second countable, you can assume G is the real line, and P is a sub-semigroup. So P is a semigroup. So it's not a group, it's not a subgroup, it's a semigroup. That means it's just closed under multiplication. It has no inverses. And I assume that it has identity element. Because if it does not contain identity, you can always throw in the identity and make it a semigroup which contains identity element. So what are the examples? So let us take G to be real line and P to be the positive real line. If you add two positive numbers, you still get a positive number. So that's a semigroup. That's one example. So what is another example? You can look at the discrete setup also. So G is integers and P is natural numbers. So if you add two natural numbers, you still get a natural number. So P is a sub-semigroup. The third condition is that the interior of P should be dense in P. These are all topological conditions, but you can ignore these topological conditions for this talk. So you have a group, bigger group G, and you have a semigroup G. You have a sub-semigroup P. Okay. So the one parameter is what I said just now. G is R and P is the positive real line. So what is multiparameter? In the multiparameter, G is Rn, the Euclidean space Rn, and P is the first quadrant. That is all those entries whose coordinates are all non-negative. So if you look at the first quadrant, that will form a semigroup. So that is multiparameter. Okay. Okay. So what is an E0 semigroup? So an E0 semigroup is actually a family of endomorphisms on B of H. What is B of H? H is the Hilbert space. B of H is the set of all bounded linear operators on H. So you can add two bounded linear operators, you can multiply two bounded linear operators, and the adjoint of a bounded linear operator is a bounded linear operator. So the set of bounded linear operators form an algebra. So you look at, for each x in P, you have an endomorphism of BH. So it's a family alpha equals alpha x, where for each x, alpha x is a unital normal star endomorphism of BH. So it's a unital morphism, which means alpha x of 1 is 1 alpha x of identity is identity. It's a star endomorphism. What is endomorphism? Endomorphism means it preserves the algebraic structure. Alpha x of a plus b is alpha x a plus alpha x b. Alpha x of ab is alpha x a times alpha x b, and so on. And normal, what is normal? Normal here means alpha x is a map from BH to BH. Normal means it's continuous with respect to a certain topology. And BH has a topology which is called the strong operator topology or the weak operator topology, and it should be continuous with respect to that topology. Okay. So an E0 semigroup is a family. It's a family of endomorphism. For each x, and I have given you an endomorphism alpha x. And what it should satisfy? Alpha x composed with alpha y should be alpha xy. That means x going to alpha x should respect the semigroup law. And then third property is that it should be continuous in x. So x going to alpha x is a map. It's a map from T to endomorphisms of BH. And it is continuous with respect to that. And that map is continuous. And that continuity condition is the third condition. So for every psi and eta in H and A in BH, the map x going to alpha x a psi eta is continuous. The classical case, the one parameter case, is when G is R and P is 0 infinity. Okay. When G is Rn and P is R plus n means when G is k copies of R and P is k copies of 0 infinity, that's called multiparameter case. So the one parameter case was dealt by Arveson and Powers, and we have started doing the multiparameter case and looked at what happens, what goes wrong or what goes right in the multiparameter situation, and certain interesting things, certain interesting differences appear between the one parameter and the multiparameter case. Okay. So we want to study E0 semigroups up to a natural equivalence relation. So what is the equivalence relation that I should put? So suppose you start with an E0 semigroup alpha. That's an E0 semigroup on BH. And then I can perturb alpha by a certain unitary. So you perturb alpha x by a certain unitary ux. So you define, for every x, you have an endomorphism alpha x. I define a new endomorphism beta x. Beta x of A is ux alpha x a ux star. Then this will, because ux is a unitary, this will obviously become an endomorphism. And when this will be an E0 semigroup, precisely when ux satisfies certain condition, and that condition is called a cocycle condition, which is ux alpha x uy is ux plus y. It should be uxy, not ux plus y, because the multiplication is xy, not x plus y. So ux alpha x uy should be ux plus y. Then you can perturb your alpha x by conjugating with that unitary ux and define a new E0 semigroup beta x, which is ux alpha x ux star. And this beta is called a cocycle perturbation of alpha. Okay, and we don't distinguish between two E0 semigroup if one is a cocycle perturbation of another. And if you have two E0 semigroup acting on different Hilbert spaces, we first bring them to a common Hilbert space and compare whether they are cocycle perturbations of each other or not, after bringing into a common Hilbert space. Okay. Okay. So are there any examples, or are the examples interesting? These are the questions that one must ask. And let me first give an example. So for this, I need the notion of the symmetric Fock space and the Weil operators. So for a Hilbert space H, gamma H is the symmetric Fock space. So how to define the symmetric Fock space is, so you look at H and then H tensor with H, and then H tensor with H tensor with H. So look at H and then look at direct sum H tensor with H, direct sum H tensor with H tensor with H, and so on. So the third copy is three tensors of H, and the fourth copy is 4 tensors of H. So that will give you the full Fock space. And then to get the symmetric Fock space, you find the symmetric tensors. In the tensor product, you find only the symmetric tensors and take that direct sum. That is called the symmetric Fock space. In the symmetric Fock space, you have the set of exponential vectors, which is for every u in H, you can define the exponential vector E of u, which is summation n equals 0 to infinity u tensor n by square root of n factorial. The square root of n factorial is made so that inner product exponential of u times inner product exponential of v is e power inner product qv. So, so the properties of the exponential vector is that the exponential vectors form a total set, and inner product of EU with EV is exponential of inner product QV. So, and then the Weyl operators are defined in gamma H. So for U in H, there exists a unique unitary operator denoted W of U, such that W of U, whose action on the exponential vector, W of U E of P is e power minus norm U square by 2 minus inner product QV exponential of u plus v. So what you do is you translate exponential of v to exponential of u plus v. But if you translate, the inner products don't match. So, I mean, it should be a unitary operator. W of u should be a unitary operator. So if you translate E of E to E of u plus v, the inner products don't match. So you put a scalar in front to adjust the inner product. That's why the scalar is coming. So it's basically a sort of translation action. So H acts on gamma H through the Weyl operators. And an important fact is that the von Neumann algebra generated by W of U is sigma weakly dense in B of gamma H. That means if you look at the strong closure of W of U, that is dense in the bounded operators on gamma H. Okay, so this is one thing that I need. So this is about the symmetric Fock space and the Weyl operators. And another important notion is the notion of isometric representation. So let V be a map. So V is a map from P to B of H. So for every element X in P, I have an operator Vx, which is an isometry. Vx is an isometry, and it should be a representation, meaning Vx, Vy should be Vxy. So for every X in P, Vx is an isometry, and Vx, Vy is Vxy. Such a thing, if V satisfies A and B, V is called an isometric representation. Of course, we are dealing with some sort of topology all the time. There is some sort of topology involved. So you require that the association V going from X going to Vx is actually continuous. So for every psi in H, X going to Vx psi is continuous, should be continuous. Okay, such a thing is called an isometric representation of P. Are there good examples of isometric representation? Yes, there are quite a lot. And this is where the difference between the one parameter theory and the multiparameter theory comes. In the one parameter theory, that is when G is R and P is 0 infinity, there are only countably many isometric representations. You can actually write down all the isometric representation. In the multiparameter theory, there are actually uncountably many, and it is impossible to write down all isometric representation. So in the one parameter theory, you can write down all isometric representation. In the multiparameter theory, you cannot write down all isometric representation. Writing down means writing down in a very good way. Is there a good way to write down isometric representation in the one parameter context? Yes. So what is that? So here is how it comes. Here is a Hausdorff example. So let G equals RD and P be a closed convex cone in RD. So if D is 1, that is one parameter situation. Okay. If D is 1, that is one parameter situation. So A is a measurable subset of RD such that A plus P is contained in A. That is, A is P invariant. So if G is R and P is 0 infinity, what are the possible choices of A? A plus 0 infinity should be contained in A. That means if I take an element in A, and if I take an element X in A and T in P, that is, if I take an element X in A and a positive number T, X plus T should be in A. So if X is in A, X plus T should be in A. That means If X is in A, all things which are bigger than A should be in A. So it is not difficult to work out how a typical capital A will look like. A typical capital A will look like an interval which stretches to infinity. Okay, so by translating, you can assume that A is just P. Okay, so given, but you cannot write down, just 1 minute. You cannot write down if D is, so for example, so I can if some students are attending, I can give this as an exercise. I'm getting a call. Is anyone? Just 1 minute. Hello. Sorry. I'm sorry. I thought somebody from. Okay, so I can give as an exercise here that find all subsets A when D is 1. That is in the one-dimensional case. Find all subsets, all possible subsets like this. You can show that such subsets are precisely an interval which stretches to infinity, which goes to the right side of infinity. That means A comma infinity. Such a subset should be of the form A comma infinity. Whereas when D is greater than or equals to, in the two-dimensional case, it's impossible to write down. It's impossible to count them or enumerate or something like that. There are uncountably many possible choices. Okay. Even in the one parameter, there are uncountably many, but I don't distinguish two things if one is a translate of another. Okay. So up to a translate, the only possible choice of A is 0, infinity in the one parameter case. In the multi-parameter case, there are so many choices of A. So that's the first thing that you have. Once you have such an A, you can build an isometric representation out of it, because P leaves A invariant. So P is acting on A. So P will act on functions of A also. So look at functions of A which are square integrable, that is L2 of A. And for X in P, you define an isometry Bx, which is given by Bx f of y is f of y minus x if y minus x is in A, and 0 if y minus x is not in A. What I am doing is that I'm just translating. You have a function f. I'm just translating it by x. I'm just translating it by x. But the thing is that y minus x need not have to fall in A. So when it falls in A, you define it to be the value of f at y minus x. If it does not fall in A, you define it to be 0. This is the shift action. You are just shifting by x. So this is the shift semigroup, and this is a strongly continuous semigroup of isometries, or it is an isometric representation. Because there are so many possible choices of A in two-dimensional case or higher dimensional case, there are so many possible choices of isometric representation as well. Okay. So what we can do with an isometric representation, once we have an isometric representation, we can build as E0 semigroup through the second quantization construction. So V is an isometric representation of P on H. So it's a strongly continuous semigroup of isometries. Strongly continuous semigroup of isometries is another term for an isometric representation. So start with a strongly continuous semigroup of isometries on the Hilbert space H. Then there is an E0 semigroup. The E0 semigroup, alpha x. Alpha x is an endomorphism of B of bounded operators of some Hilbert space. So look at B of gamma H. There is an endomorphism alpha x. Inside B of gamma H, you have the Weil operators. So alpha x acting on the Weil operators is Weil of Vx, okay, for x in P and u in H. This E0 semigroup is called the CCR flow associated to the isometric representation B. In the one parameter case, the CCR flows are completely understood because the isometric representation is completely understood. In the multi-parameter case, the CCR flows themselves are not completely understood because the isometric representation in the multi-parameter case themselves are not completely understood. So that's the one difference. Okay. Let me go next. So similar to the CCR flow, there is something called car flow, which is on the anti-symmetric Fock space. So the last time we looked at symmetric Fock space, which is made of symmetric tensors. You take the tensor product and take direct sum of all such symmetric tensors. So gamma AH is the anti-symmetric Fock space here. It is the direct sum of vectors of the form psi1 with psi2 with psi n. Okay, you take direct sum of elements of these forms. Such vector psi1 with psi2 with psi n is called an n particle space, and the inner product of two n particle spaces is given by this formula. That is, if you take an n particle space with psi's involved, and if you take another n particle space with eta's involved, then take the inner product psi I eta j, that will give you a n cross n matrix, and take this determinant. That is the inner product. This is the inner product of two n particle vectors. And a n particle vector and an m particle vector, if n and m are different, they will be orthogonal. And you take direct sum of all such vectors and take its completion and so on and so forth, you get a Hilbert space. And that Hilbert space is called the anti-symmetric Fock space. And you can define, just like we define Weyl operators on the symmetric Fock space, you can define the creation and the annihilation operator. I'm just defining the creation operator here because the annihilation operator will be the adjoint of a creation operator. So C of psi on n particle vector is you create a new vector psi here. So C of psi acting on psi1 with psi2 with psi n is psi wedge acting on psi1 with psi2 with psi n. So psi is inserted in front. So it creates. So C of psi is a creation operator. Then given a strongly continuous semigroup of isometries, just like we define CCR flow on the symmetric Fock space, we can define CAR flow on the anti-symmetric Fock space, whose action on the creation operator is given by this formula. So beta x C of psi is C of Vx psi. So this is called the CAR flow, and that's called the CCR flow. And in the one parameter case, both CCR and CAR are the same up to cocycle conjugation. So beta V will be a cocycle perturbation of alpha V, whereas in the multiparameter case, they won't be true. Okay. So I have defined what an E0 semigroup, and I have given two examples. One is the CCR flow and another is the CAR flow. So how much we can imitate the one parameter theory, and why multiparameter theory is interesting? It's because of the following reason. The basic theory stays true, okay? But there are significant differences. So what do I mean by saying the basic theory stays true? The basic theory between the one parameter theory and the multiparameter theory there is a basic uniformity between them, but there are significant differences if you start analyzing examples. So what is the basic theory? Okay, so our main objective is to understand all E0 semigroup, not just particular classes of example. By the way, even in the one parameter situation, understanding all E0 semigroup is not complete yet. There are still important problems in one parameter theory, and classifying one parameter E0 semigroup completely is not possible. What I said was classifying the CCR and the CAR is over in the one parameter theory. They are particular examples of E0 semigroups, but classifying all the examples of E0 semigroups is not over even in the one parameter theory. But in the multiparameter theory, classifying CCR and CAR itself is not over. So that's something one has to keep in mind. So how? Okay, it's a complicated task classifying one parameter theory, but we can try to find some invariants in the hope that they form some sort of a complete invariant and try to use the invariants to compute. For example, if you try to classify topological spaces, what are the things that we will compute? We will compute the fundamental group, we will compute the homology groups, and so on and so forth, right? If you want to say that two topological spaces X and Y are not homomorphic, we compute the fundamental groups pi1x and pi1y and see whether they are same or not. If they differ, then you can say that X and Y are not homeomorphic. If they are same, you cannot say anything more. Such kind of invariants we can try to find here and try to use it here also. So one such invariant is the notion of product system, which carries over in complete generality, and that is due to Arverson. So start with an E0 semigroup, and for X in P, I collect the set of operators T in BH, which intertwines alpha X and A, which intertwines the identity representation and alpha X. So that's the equation. Alpha X A T is TA for all A in BH. So alpha X is an endomorphism of BH. So an identity, you can think of identity also as an endomorphism. So define beta XA as identity. So alpha XA T is T beta XA. So the collection of all T which intertwines alpha X with the identity map. So this EX is called the intertwining space of alpha X. Okay. Why is it important? Because it's a Hilbert space. How it becomes a Hilbert space? Okay. So take two operators S and T from EX. S and T are basically, first of all, operators. Okay. On the set of operators, there is no inner product as such, but here it becomes an inner product space. So take two operators S and T from EX and look at T star S. Because S intertwines alpha X with identity and T intertwines alpha X with identity, T star will intertwine identity with alpha X, and if you work it out, you will see that T star S will intertwine identity operator with identity operator. That means that T star S commutes with all operators. So if you take a matrix which commutes with all other matrices, you should think of operator as some infinite matrix. If you have a matrix which commutes with all matrices, what can one say about that matrix? That matrix has to be a scalar, right? So T star S is a big matrix and it commutes with all matrices. So it has to be a scalar, and that scalar I denoted by ST. Then this defines an inner product structure on EX. And EX will become a separable Hilbert space with respect to this inner product. Okay. Not only you have a Hilbert space, for every X you have Hilbert space. Okay. And you have a bundle of Hilbert spaces. So call that bundle of Hilbert spaces as E alpha, which is the disjoint union EX. So there is a product rule also. So an element in E alpha is basically X comma S, where S is coming from EX. Okay. X comma S is the element here, which lies in the X component. So X comma S, Y comma T is XY comma ST. So if you take S in EX and T in EY, ST will be in EXY, and there is a product rule. So and moreover, this product is not just an ordinary product. This product S comma T goes to ST. So from EX tensor EY to EXY, S tensor T goes to ST is actually a unitary operator. You can prove that this is a unitary operator. And so for every X, you have a Hilbert space EX, and you have a bundle of Hilbert spaces. You have a product structure, and the product is just not an ordinary product, it's an associative product, and the product is such that S tensor T going to ST is a unitary. So this structure is an invariant for an E0 semigroup. Okay, so if two E0 semigroups are isomorphic, this whole structure, by this whole structure I mean this bundle of Hilbert spaces, is an invariant, and this bundle of Hilbert spaces is called the product system associated with alpha. So E alpha is called the product system associated with alpha. Okay. The bundle E alpha together with all the structures that I have imposed is called the product system associated with alpha. So starting with the E0 semigroup, I can define a bundle of Hilbert spaces. The bundle is fibered over the semigroup P, and it has a product rule, And this bundle of Hilbert spaces together with the product rule is called the product system of the E0 semigroup. And any such bundle of Hilbert spaces with the associative product rule as above is called the product system. Why is this important? This is important because of the following theorem. Okay, sorry, let's see an example of this. I should demonstrate an example of what these Hilbert spaces are for a specific example, right? So after that, we will see why this is important. So V is an isometric representation of P on H, and alpha is the CCR flow. So recall that alpha is the CCR flow, which means that, let me go back to the definition. So it is acting on the, so this is the definition of the CCR flow. It's acting on the bounded operators of the symmetric Fock space, and its action on the Weyl operators is Weyl of Vx. Okay, so I want to work out the product system of this product system for this E0 semigroup. And let me go one more slide back to show you what are the exponential vectors. Oops. So on the symmetric Fock space, you have the exponential vectors, which is just defined just like our usual exponential. So u power n, the power n, you should think of them as u tensor u. And instead of n factorial, you have square root of n factorial. So the reason behind this appearance of the magical square root is because you want to have this formula. Exponential of u, inner product exponential of v is exponential of inner product uv. I mean, if you can define without the square root also, but then you won't have this formula. So people define it with the square root so that they have this nice formula to work with. That's the reason behind this. Okay, so let me go back to the product system for a CCR flow. So I want to, so recall, to describe the product system, I need to tell you what the Hilbert space is and what is the product rule. Okay. Okay. So alpha is the CCR flow associated to V. Then for every x, Ex is the symmetric Fock space of kernel Vx star. Okay, Ex is the symmetric Fock space of kernel Vx star. The right hand side is a Hilbert space. So the Hilbert space Ex can be identified with gamma of kernel Vx star. I have to tell you the product rule, which means I need to tell you how to multiply two vectors. But exponential vectors are total. So that's a generating set. Total means it sort of generates. So to define multiplication, it suffices to know how multiplication is behaved on a generating set. So you just need to know how to multiply exponential vectors. So exponential of psi in a times exponential of eta is exponential of psi plus Vx eta. For psi in kernel Vx star and eta is kernel Vy star. So this is the product system of the CCR flow. One can work out the product system of the car flow also, but I have not included this in my slide. And why is the product system important? Because of this theorem. This theorem was proved originally for the one parameter case by Arveson, and Arveson's proof just goes through for any semigroup, not necessarily one parameter semigroup. So if you have two E0 semigroup, then alpha is cocycle conjugate to beta, if and only if their product systems are isomorphic. Okay, if the product system of alpha and the product system of beta are isomorphic, then alpha is cocycle to conjugate to beta, and if alpha is cocycle conjugate to beta, their product systems are also isomorphic. So the product system is determines completely the E0 semigroup. Okay, this raises the following question. See, I have defined a product system given an E0 semigroup. Given an E0 semigroup, you can always define a product system. Suppose I start with the product system. That means for every x, Ex is a Hilbert space, and there is a product rule. Ex times Ey, Ex, if I take an element in Ex and an element in Ey, I have a product which goes to Exy. So you have a bunch of Hilbert spaces and you have a product rule on them. Can you define an E0 semigroup so that this product system is isomorphic to the product system of a given E0 semigroup? So this is the question of Arveson. This is Arveson's. This is the basic question in this theory. It's not completely solved for all semigroups, but the solution is known for a few semigroups. So here is the original proof, original thing due to Arveson. Arveson proved it when G is R and P is 0 infinity. And the first proof was due to Arveson. It was a very complicated proof. It's very long, quite technical, and so on. Then a shorter proof was found by Skyday, and Arveson himself found a very short proof for this one-dimensional case. Then, along with the student, I worked out the higher dimensional version. That is when G is RD and P is a closed convex cone. That is when G is RD and P is R plus D. If G is R2 and P is the first quadrant, then Arveson's shorter proof can be imitated in this higher dimensional setting also. That was basically the work with Murugan. Okay, so Arveson's question has an answer if G is RD and P is a cone. So how far one can go? So we can go. So Arveson's proof works perfectly well in the situation that I have given as condition C, as item C. That is, suppose G is abelian and P has the Archimedean property. So what do we mean is that you can define an order. So X is less than or equal to Y if Y minus X belongs to P. So once you have a semigroup, that semigroup defines an order on G. And if that order has an Archimedean property, that means there should be an A, or more precisely, the correct term is order unit. I'm calling it as an Archimedean property. So there should be an A such that whatever element X that you give, I can find the natural number N such that NA is greater than or equal to X. So you should be able to solve this equation for a large N. That is what Archimedean principle is, right? So given a positive number A, I can always find a natural number such that NA is greater than or equal to X. So if this Archimedean property holds, then Arveson's question has an answer. Basically, Arveson's proof works. Arveson's proof works in this situation also. But there are examples which does not have Archimedean property. So what is the most basic example? You look at your semigroup natural numbers, but instead of addition, you look at with multiplication. This will not have Archimedean property because, and what is the group involved? You take natural numbers, you take quotients of natural numbers, you get rationals. So the group involved is positive rationals and the semigroup involved is natural numbers. The semigroup is natural numbers with multiplication. The natural numbers has infinitely many primes. So that's why if you think about what Archimedean property means in that situation, it means that if Archimedean property holds in that situation, it means that there are only finitely many primes, which is a contradiction. Since there are infinitely many primes, Archimedean property does not hold. So one would like to know the answer to Arveson's question, whether every product system over natural numbers with multiplication, does it come from an E0 semigroup? Natural numbers with addition, yes. Natural numbers with multiplication, it's an open question. Okay, suppose I have given you a Hilbert space over natural numbers and there is a product rule. Does it come from an E0 semigroup? If the product rule is addition, I mean, if the semigroup is natural numbers with addition, yes. If the semigroup is natural numbers with multiplication, then we don't know. Okay, so far the answer is not. Okay, so this is what I mean by saying that the basic theory stays intact. That is, In the multiparameter situation, that is when G is RD and P is when G is R2 and P is the first quadrant, the bijection between E0 semigroups and product system, there is a bijection between them in the one parameter theory, and the same bijection holds in the multiparameter theory also.
So
yeah,
for this G is equal to Q plus and P is this natural number minus 0 with multiplication. So can you give example of E0 semigroups?
Yeah, you can take the same. I mean, that same E0, the CCR and CAR is always there.
Okay.
And you can define isometric representations indexed by natural numbers with multiplication. I mean, the CCR and CAR E0 semigroups are always there. But I don't know how to construct a product system. First construct a product system and then an E0 semigroup. That's a bit tricky.
Okay.
Yeah,
so
we don't.
Are there classifications in this case up to isomorphism of all E0 semigroup for this G is equal to Q plus?
No,
you are saying
we don't. No, there is a no. Wait, if P is natural numbers with addition, then there is a classification. It's just there are only countably many, because natural numbers with addition is cyclic, and you can classify them. But with multiplication, it's not possible, and there is no known classification.
Okay.
Yeah. So this is what I mean. I mean, what I mean that the basic theory stays intact is, at least in the continuous case, when you replace the real line by R2 and the half line 0 infinity by the first quadrant, the bijection between product system and E0 semigroup is true. Okay, and that was Murugan's thesis basically. And so the study of product system and the study of E0 semigroups in the multiparameter case is the same, just like in the one parameter case. Okay. So I will illustrate some differences. So for the rest of the talk, P will be a closed convex cone in RB. So you can assume that D is 2. So you can assume it's R2, and you can assume that P is the first quadrant. Okay, so P is x comma y, x greater than or equal 0, y greater than or equal 0. So what are the some of the differences? So there I'm going to throw in a few jargons. Some of them I have explained. So decomposable product system need not necessarily have a unit. All these 1, 2, 3, I have listed 3 properties. So decomposable product system need not necessarily have a unit. So it is possible. This is not possible in the one parameter theory. One is not possible in the one parameter theory. And the opposite of a CCR flow need not be cocycle conjugate to itself. Again, 2 is not possible in the one parameter theory, whereas 2 is possible in the multiparameter theory. The CAR and CCR need not be the same. In the one parameter theory, the CAR and the CCR are the same. And the last thing was proved by Srinivasan of CMI. So the CCR flow and the CAR flow need not be the same in the multiparameter theory. So I will explain in the rest of the talk what I mean by 2. Okay. I want to say that in the higher dimensional case, the opposite of a CCR flow need not be cocycle conjugate, need not be isomorphic to itself. So I need to explain, I have already explained what a CCR flow is. I need to explain what I mean by an opposite of a CCR. Okay. So alpha is an E0 semigroup on BH. Look at the product system, which is E, the bundle of Hilbert spaces, which is the disjoint union of EX, X comma T, X in P and T in EX. That's the product system. The product structure is X comma S, Y comma T is X plus Y, ST. So this is the product rule. How do we define the opposite of a group? You just interchange the order of the product, right? So we define the opposite of a product system by interchanging the order of the product. So we define a new product by defining x comma s, y comma t is x plus y, ts. Instead of st, I put ts. So then this will give another product structure, and with this product structure, I call that you will have a product system. And because product systems in the multiparameter theory, product systems also come from E0 semigroup. There will be an E0 semigroup whose product system is isomorphic to E opposite. So that's called the opposite of the product system. Okay. So the product system E together with this new product structure is called the opposite, and I denote it by E opposite. If E is isomorphic to E opposite, I call the product system symmetric. If E is not isomorphic to E opposite, I call the product system asymmetric. What do we have in the one-dimensional case? That is when P is 0 infinity, we have the following. So one parameter CCR flows are symmetric. And this is because one parameter CCR flows are completely understood. And if you look at the classification due to Arvesen, it becomes very apparent. And constructing asymmetric E0 semigroups was an extremely tough problem in the one parameter theory, and that was done by Cyrilson using probabilistic techniques. So constructing an asymmetric E0 semigroup in the one parameter theory was a tough problem. But in the multiparameter context, asymmetry is observed even with CCR flows. This is because of the reason that I explained at the beginning, that in the one parameter theory, isometric representations are easy to understand. Whereas in the multiparameter theory, isometric representations themselves is a complicated object. So that's why asymmetry is observed even with CCR flows in the that's a philosophical reason. That's why asymmetry is observed even with CCR flows in the multiparameter theory. But I will give an example. So here is the theorem. First of all, the opposite of a CCR flow is a CCR flow, but it may not be the same CCR flow. Okay. So what do I mean? So here is the idea of the proof. So start with an isometric representation of P on H. Then you can dilate that into a unitary representation. So I think I have 10. Just give me a second. I have 12 minutes. So
yeah, yes.
Yeah. So you can dilate an isometric representation to a unitary representation. So what do you mean by dilating? So if you have a semigroup, so you should think of isometric representations as semigroup actions. Okay. So if you have a semigroup acting on an object, so acting on a set. For example, let us take our most basic example. Natural numbers is acting on natural numbers by addition. This action, natural numbers, is acting on natural numbers by addition. This action can be extended to a Z action. That's how we construct integers, right? To construct integers, we start with natural numbers. We consider n cross n, put an equivalence relation, and so on and so forth. So if you look at the natural numbers action restricted to natural numbers, that is not invertible. So if you take x going to x plus 1, that is an injective map when restricted to natural numbers. But that becomes a bijective map when restricted to integers. So you can extend the set. You can extend the set into a larger set and make it bijective. In a similar way, if you have an isometry on a Hilbert space, an isometry is just something which preserves distances, which preserves inner product. It need not be surjective. The difference between isometry and unitary is because is just the surjectivity. It need not be onto. But what we can do is we can enlarge the Hilbert space into a bigger Hilbert space and make it a unitary. So that's what we can do. So we can dilate B to a unitary representation, and we can do that in a minimal way. That is, the enlargement is minimal, which means that any other enlargement, this minimal enlargement is inside it. Okay. You can dilate it to a unitary representation of the whole group on Heights tilde. and you can put your Hilbert space H into H tilde. This is exactly the same as constructing integers from natural numbers. Okay, there is nothing beyond statement one. Statement one. So H is invariant under the semigroup P. So its ortho complement will be invariant under minus P. Okay, so I can define a new isometric representation by defining WA to be U minus E, restricted to K. I mean, H is invariant under UA, K will be invariant under U minus E. So look at natural numbers. When the natural numbers 1, 2, etc., that will be invariant under addition by positive direction, whereas minus n, its complement. Now, its complement is minus n. Its complement will be invariant under subtraction, right? So it's the same thing. So you can define a new isometric representation by defining W to be U minus A on K. Then this will be an isometric representation on K. And the theorem is the opposite of alpha V, the opposite of the CCR flow alpha V is isomorphic to the CCR flow alpha W. So opposite of alpha V is alpha W. Where how is alpha W computed? You take you dilate first of all V to a unitary representation U and take its ortho complement. So the opposite of alpha V is alpha W, and we call W the opposite of V and denote it by V opposite. And what is the explicit isomorphism? The explicit isomorphism is given by this formula. So I'm skipping it right now for lack of time. So and here we have the theorem. So if you have an isometric representation, these are jargons, pure isometric representation. The CCR flow, when is the CCR flow symmetric? The CCR flow is symmetric. That means it is isomorphic to its opposite. We know the opposite of alpha V. The opposite of alpha V is alpha V opposite. They are symmetric if and only if V and V opposite are unitarily equal. The reason 1 and 2 are equivalent is because if alpha V is isomorphic to alpha V opposite, if for two isometric representation V and W, alpha V is isomorphic to alpha W if and only if V and W are isomorphic. So that's another theorem which I am skipping. So alpha V will be symmetric if and only if V and V opposite are unitarily equal. Okay. So let us calculate V opposite for the examples that I gave at the beginning. So let me recall the example. So A is a subset of Rd. We say that A is a P space if the subset A is closed, non-empty and proper. Proper means it's not the whole space. And A plus X is contained in A. So when for every X in P, that means P is acting on A. Because P is acting on A, P will act on functions on A. So P will act on L2A by isometries, and the associated isometric representation I denote it by VA, and the associated CCR flow I denote it by alpha A. So if you work out, so for any P space, there is an isometric representation VA. Okay, so if you work out the opposite of VA, so you have to dilate first of all what is the dilation of VA. If you dilate that, if P is acting on A, I want to dilate A into a larger set. So if I want to dilate A into a larger set, A is contained in Rd and Rd is acting on Rd. So the larger set will be Rd. So the dilation will be acting on Rd. Okay. So P is acting on A, its dilation will be acting on Rd. So using that, you can work out explicitly what the opposite is, and the opposite will turn out to be, you have to take the complement and subtract something. You have to take the complement and subtract. So here is the theorem. So finally, if you put the CCR flow alpha A is symmetric if and only if minus A is a translate of interior of A complement. So if you take A equals P, that is, if you take A equals R plus 2, if you take the first quadrant, you can easily see that this condition is violated. This condition is violated because if A is the first quadrant, what is interior of A? Interior of A is the first quadrant itself, the open quadrant. Its complement will be the union of the other three quadrants, right? So one quadrant cannot be a translate of three quadrants. A is one quadrant. Interior of A complement is is the union of three quadrants. So one quadrant cannot be complement of three quadrants, right? Cannot be union of three, cannot be a translate of three quadrants. That's why this condition is violated if you take A to be the first quadrant. Whereas if you take A to be the half plane, if you take A to be the right half plane, just like this, then this condition will be true. So you get both symmetric and asymmetric CCR flows. So you get both symmetric and asymmetric E0 semigroups, and that is observed even with CCR flows. So this is one difference that occurs between the one parameter theory and the multi-parameter theory. And there are quite a lot of differences, and that's why it makes this worth studying, and it makes this thing it makes it worth studying. So thank you.
Thank you very much, Sundar, for this wonderful talk.
Thank you.
Are there any questions?
Yeah, I have a question.
Yeah.
Okay. First of all, thank you very much for the nice talk. And so my question is that about P, your P, is it necessary that P should be an algebraic group, a topological group, or
G should be a topological group and P should be a semi-group? I mean, you can assume that G is discrete and P is discrete. You can assume that G is a discrete group. You can forget all topology also. But if you are working with a topological group, then you need some sort of Haar measure and things like that. So to do analysis, you need some sort of Haar measure. So for that, you need to assume some topological. It should be a locally compact group.
And one more question regarding the Artson question.
Yeah.
Some point you mentioned that G is abelian group. So why the abelianness is important to that particular situation, and P has the Archimedean property. So could you say?
Yeah, the proof. I mean, how much you can carry Arveson's proof was Arvesson first of all found a very complicated proof, and then I will go to that slide. You can see the slide.
Yeah, let's see. Yeah.
Yeah. So Arveson's first proof was very long, and then it was shortened by the proof was not shortened. A different proof was found by Skyday, and Arveson himself found a different proof, very short proof. It is just 5 pages long. So how much we can imitate 5 pages long? That thing was, we could do the imitation when P is a closed convex cone, and that same imitation goes through for G is abelian and P has the Archimedean property. When these two properties, when the commutativity assumption breaks down, that proofs breaks down. I'm not saying that. So we don't know how to manage that proof. So we don't know how to, or we don't know a new proof also. So that's an open question. So it's not in one step, in several steps, that commutative assumption, if it breaks down, the whole proof will break down. So it was very crucial.
Okay, thank you.
Yeah, only when I can explain if I give a talk on that theorem. So rather than I will explain.
Yeah, we'll be very happy. Yeah, when the situation is normal, you can visit us. We'll be very happy.
I can give a more.
Okay. Thank you.
Thank you.
Are there any other questions? So if not, let's thank the speaker again. So it was very, very precise and wonderful talk.
Yeah, I thank the organizers again, and I thank Shurat knows Biswas and a lot of other people who have written to me, and it's great pleasure to give a talk at SRM, and hopefully I will come there also. So thanks a lot again.
Okay, Sundar. Have a nice day.
Yeah, have a nice day. Thanks.
Okay.
I would like to thank our ITKM people for conducting this session very smoothly. I also thank all the participants and my colleague. So thank you. I also thank Professor Sundar for agreeing to give a talk in our departmental seminar. We'll be very happy. We will visit.
Yeah, we hope to hear from him in future many more times.
Okay. Sure.
Thank you.
Thank you. I'm leaving now. Thank you.